More than 13 billion years ago, when the universe was still in its infancy, a black hole was already growing at the center of a tiny young system. James Webb has now revealed evidence that this black hole may have become massive before its galaxy was fully formed. Tonight, the journey follows that ancient light across cosmic time to uncover how such an object could exist so early. If calm science documentaries help make the night a little quieter, please like the video and subscribe for more journeys into the universe. The light associated with this discovery begins its journey when the universe is still very young. The cosmos is about 700 million years old, only a fraction of its present age of 13.8 billion years. Space already extends far beyond any single galaxy, but large structures in the nearby universe are still developing. Matter has been gathering under gravity for hundreds of millions of years, forming dark matter halos, clouds of gas, young galaxies, and the first generations of stars. The universe is no longer the nearly uniform mixture that follows the Big Bang. It is becoming a web of growing structure with dense regions connected by long filaments and separated by expanding areas of lower density. This era lies within a broad period often called cosmic dawn. The name describes the time when the first stars and galaxies bring new sources of light into a universe that had previously been dark at visible wavelengths. Long before these stars appear, ordinary matter cools enough for electrons and atomic nuclei to combine into neutral atoms. That transition occurs several 100,000 years after the Big Bang. Afterward, the universe enters a long interval with no stars yet shining. Gravity continues to act slowly on tiny variations in density. Regions containing slightly more matter attract additional material. Dark matter, which does not emit or absorb light in the ordinary way, provides the gravitational framework. Hydrogen and helium gas fall into these growing concentrations and gradually become dense enough for stars to form. By 700 million years after the beginning, this transformation is well underway. Galaxies exist, but many are small, irregular, and rapidly changing. Their stars are often young. Gas flows through and around them, sometimes feeding new star formation, and sometimes being heated or pushed outward by energetic processes. Mergers between small systems are common because the cosmic structures have not yet settled into the more mature forms seen nearby. The boundaries of a young galaxy can be difficult to define. Stars may occupy only a compact central region, while gas extends farther outward, and the surrounding dark matter halo can be much larger than either. The chemical composition of the early universe also differs from the composition found much later. The Big Bang produces mainly hydrogen and helium along with very small amounts of a few lighter elements. Most heavier elements are created later inside stars and during stellar explosions or other energetic stellar events. At this early time, some regions have already been enriched by earlier generations of stars, while others remain chemically primitive. The amount of elements heavier than helium varies greatly from place to place. This uneven enrichment becomes an important record of how much stellar activity has already occurred in a particular region. Radiation is also changing the wider environment. The first luminous objects produce energetic, ultraviolet light capable of removing electrons from neutral hydrogen. This process, known as rayonization, gradually changes much of the gas between galaxies from a neutral state into an ionized one. Reionization does not occur everywhere at the same moment. It proceeds unevenly as growing bubbles of ionized gas form around early sources and expand. At roughly 700 million years, observations indicate that this transition is still in progress. The history varies with location, and astronomers continue to refine the timing and pace of the process. Against this evolving background, distance and time become closely linked in observation. Light travels at a finite speed, so extremely distant objects are seen not as they are in the present cosmic age, but as they existed long ago. When radiation begins traveling from a source during cosmic dawn, it spends more than 13 billion years crossing expanding space before reaching telescopes near Earth. During that journey, the expansion of the universe stretches the wavelength of the light. This stretching is called cosmological redshift. Light that begins at visible or ultraviolet wavelengths can arrive at much longer infrared wavelengths, placing ancient objects within the range where the James Webb Space Telescope is sensitive. Redshift is not simply a change in color. It provides a way to connect observed light with the history of cosmic expansion. A high redshift indicates that the radiation has been stretched substantially during its journey. Astronomers combine redshift measurements with cosmological models to estimate how long ago the light was emitted. For objects from the era near 700 million years after the Big Bang, the redshift is around 7. The relation between redshift, age, and distance depends on measured properties of the expanding universe, but the general picture is well established. The scale surrounding such an ancient object is immense. The light crosses regions that evolve continuously while it travels. Galaxies grow clusters, assemble stars, form and die, and the average expansion of space continues. The source itself remains recorded in the arriving radiation as a view of one early moment. Modern astronomy does not watch that ancient system aging through billions of years. It receives the light that left during a particular stage of its development and reconstructs physical conditions from that limited signal. The early universe is neither empty nor fully mature. It contains an active mixture of dark matter, gas, radiation, stars, and forming galaxies. Gravity has had enough time to build compact structures, yet many of the relationships familiar in older galaxies are not firmly established. Stellar populations are still accumulating. Chemical enrichment remains incomplete. Intergalactic hydrogen is still changing its ionization state. The cosmic web continues to deepen as matter flows toward dense regions. Within this setting, the existence of very massive compact objects places strong constraints on cosmic history. Any object observed at such an early age has only a limited amount of time available for its formation and growth. The universe itself provides that clock. Roughly 700 million years separate the hot early cosmos from the light now being studied. Every process involved in assembling stars, gas galaxies, and compact masses must fit within that interval. This simple boundary makes the early universe a particularly revealing laboratory. The farther observations reach into cosmic dawn, the less time nature has available to produce the structures that appear there, and the more precisely their physical conditions can test models of how the first major cosmic systems take shape. Far in front of the ancient source along the same narrow line of sight lies a much nearer concentration of matter known as Abell 2074. It is commonly called Pandora's cluster, although it appears as a single cluster in wide astronomical images. It is not a simple, quiet collection of galaxies. It is a complicated system shaped by collisions among several smaller galaxy clusters. Each of those groups brings galaxies, dark matter, and extremely hot gas into a shared gravitational environment. Their combined mass produces one of the most useful natural lenses available to astronomers studying the distant universe. A galaxy cluster is the largest kind of structure held together mainly by gravity. Its visible galaxies are only part of its contents. Vast quantities of hot gas occupy the space between them, reaching temperatures high enough to emit strongly in X-rays. Even more of the total mass exists as dark matter. Dark matter does not shine, but its gravity affects galaxies, gas, and passing light. In Abell 2074, these components are distributed unevenly because the cluster has experienced a complex history of merging. The resulting landscape of gravity is broad, irregular, and powerful. The galaxies scattered across the cluster provide the most obvious points of light. Some appear as large elliptical systems with older stellar populations, while many smaller members occupy the same field. Between them lies the hot intra-cluster gas. This gas is extremely thin compared with ordinary air, yet it fills enormous volumes. When cluster components collide, the gas interacts, compresses, and heats. Dark matter behaves differently because it does not experience the same kind of friction through ordinary electromagnetic interactions. The separation between hot gas and gravitational mass allows astronomers to map aspects of the cluster's past and to estimate where much of its invisible matter is concentrated. The gravitational influence of this combined material extends far beyond individual galaxies. According to general relativity, mass and energy curve spacetime, light follows the geometry of that curved space-time, so a beam passing near a massive concentration changes direction. A galaxy cluster contains enough mass for this deflection to become measurable across a large region of sky. When a distant source, a foreground cluster, and an observer happen to be arranged appropriately, the foreground mass acts as a gravitational lens. This lens is not made of glass and it has no physical surface. The bending occurs throughout the curved region surrounding the cluster. Different light paths pass through different parts of the gravitational field and are deflected by different amounts because Abell 2074 has an uneven mass distribution. Its lensing pattern is more complicated than the pattern that would be produced by a single symmetrical object. The positions of galaxies, dark matter concentrations, and other mass all contribute to the final distortion. In Webb images, the effect becomes visible through numerous distant galaxies behind the cluster. Some background systems appear stretched into thin arcs. Others appear broadened or distorted. In favorable alignments, the same distant galaxy can appear in more than one location because its light reaches the observer along multiple curved paths. These shapes are not physical distortions occurring within the distant galaxies themselves. They are changes in the observed images created as the light travels through the gravitational field of the foreground cluster. Magnification is another important result. Gravitational lensing can concentrate light from a distant source so that it appears brighter than it otherwise would. This does not create new radiation, it changes how light from the source is distributed across the sky. For extremely faint galaxies in the early universe, the added brightness can determine whether an object is detectable and whether enough photons can be collected for detailed study. Abell 2074 therefore functions as part of the observing system, even though it lies naturally in space and has no connection to the telescope itself. The lens also changes apparent size. A compact background object may be stretched so that Webb receives a larger image than would be available without the foreground cluster. That effect can improve the amount of spatial information available to astronomers. At the same time, the transformation must be modeled carefully. An observed arc, or enlarged image, does not directly show the original geometry of the distant source. Researchers construct maps of the foreground mass and calculate how the cluster bends light across different positions. They can then work backward from the lensed image toward an estimate of the source's intrinsic appearance. Building such a map requires many pieces of evidence. The locations and shapes of multiple lensed galaxies help reveal the gravitational field. Images of the cluster galaxies provide information about visible matter, while observations at other wavelengths trace hot gas. Multiple images of known background sources are especially useful because their relative positions constrain the amount and distribution of mass required to bend the light in those particular ways. The resulting lens model contains uncertainties, and these uncertainties become part of measurements made for distant objects seen through it. Because the cluster is much closer than the ancient source, astronomers can treat its gravitational influence as a foreground transformation. Careful modeling separates that later distortion from the physical properties carried by the radiation itself. Able 2074 is especially valuable because Webb combines the cluster's natural magnification with exceptional infrared sensitivity. The cluster field contains a dense mixture of nearby cluster members and much more distant galaxies lying behind them. Webb distinguishes many faint sources whose light has traveled across most of cosmic history. The foreground cluster does not merely block that deeper view, its gravity opens additional observational paths by amplifying light that would otherwise be more difficult to examine. The ancient source associated with the black hole lies behind this gravitational structure from Earth's perspective. Its radiation crosses the region influenced by Abell 2074 before continuing toward the solar system. The cluster, therefore, stands as an intermediate layer between cosmic dawn and the telescope. Its mass changes the path's brightness and apparent positions of the arriving light without changing the early source into something physically different. Understanding this foreground layer is essential because the signal recorded by Webb carries two histories at once: the history written into the light when it leaves the distant object, and the later gravitational transformation imposed as that light passes through Pandora's cluster. Behind Pandora's cluster, the ancient source does not arrive at Webb as a single uncomplicated point of light. The mass of the foreground cluster bends its radiation along several different paths, and those separate paths produce three observable images of the same distant object. Each image reaches the telescope from a different apparent position on the sky, even though all three originate from one source in the early universe. This repeated appearance is one sign that strong gravitational lensing is shaping the observation. The effect begins with geometry. Light leaves the distant source in many directions. Most of those rays never reach the solar system, but some travel toward the region occupied by Abell 2074. As they pass through the cluster's gravitational field, their paths curve. Because the cluster contains an uneven distribution of galaxies, dark matter, and hot gas, the amount of bending differs from one route to another. Several of these curved paths can converge toward the same observer. The telescope, therefore, receives light that has traveled along more than one route through space. The apparent positions of the resulting images depend on the relationship between the source, the foreground mass, and the observer. A symmetrical lens can produce regular patterns, but a large merging cluster creates something more complicated. Its gravitational field changes across the sky, so each path is bent by a different amount and in a different direction. The three images of QS01 are therefore not exact visual copies placed neatly around the cluster. Their brightness, shape, and level of magnification can differ because each path passes through a different part of the lensing field. This variation is useful. If three observed points are truly images of the same source, they should share the same underlying spectral identity after the effects of lensing are accounted for. Their light should carry corresponding features produced by the same gas stars and central activity. Differences caused by magnification or distortion can then be separated from similarities that belong to the source itself. In this way, repeated images become a natural consistency test. They allow astronomers to ask whether the lens model and the physical interpretation agree with several observations that are actually connected. The paths followed by the light are also different in length. Some rays travel through longer routes through curved space-time than others, and the gravitational environment affects travel time. This means multiple images of a variable background source can arrive with delays between them. In some lensed quasars, these time delays can be measured when the source changes in brightness. For QSO-1, the main importance of the three images lies in magnification and spatial reconstruction rather than in a time delay measurement. The light still represents nearly the same ancient stage of the object viewed through three gravitationally altered routes. Strong lensing also changes the amount of detail that can be recovered. Without the cluster, the source would appear fainter and smaller. Through the cluster, some parts of the source are enlarged. This is similar to gaining access to a larger image scale, although the enlargement is uneven and must be modeled. A feature stretched in one direction may be compressed in another. The intrinsic structure can only be estimated after astronomers calculate how the lens transforms the incoming light. To perform that calculation, researchers construct a mass model of a Bell 2074. They use the positions of cluster galaxies, sets of multiply-imaged background objects, and other measurements that constrain the gravitational field. The model predicts how a source at a particular distance should be distorted, and where multiple images should appear. When the predicted positions agree with observed ones, confidence in the reconstruction improves. Remaining differences help define the uncertainty in quantities such as magnification, source size, and intrinsic brightness. For QSO-1, the presence of three images adds important leverage. A single lensed image could be interpreted with greater ambiguity because several possible source properties might reproduce one observed shape. Three images force a successful model to explain more information at once. Each image must connect back to the same location in the distant source plane, the reconstructed region where the object would appear without the lens. Their relative positions and distortions restrict the range of acceptable mass distributions in the foreground cluster. The repeated images also help distinguish the ancient source from objects that happen to lie along similar lines of sight. In a crowded cluster field, many galaxies overlap in projection, even though they are separated by enormous distances. A faint red source near a foreground galaxy can be difficult to interpret if only one image is available. When matching counterparts appear at the positions predicted by gravitational lensing, the case for a common distant origin becomes stronger. The cluster's complexity, therefore, creates both a challenge and a tool. Webb's infrared observations are particularly suited to this work because the early source is strongly redshifted. Light that began at much shorter wavelengths reaches the telescope in the infrared. The three lensed images can be compared across filters and through spectroscopy, allowing astronomers to test whether they display the same redshifted features. Agreement across these measurements supports the conclusion that the images belong to one object, rather than to three unrelated sources. The lensing configuration does not reveal the physical nature of the source by itself. It establishes how the radiation is being rearranged before observation. Once that transformation is understood, the apparent brightness can be corrected toward an intrinsic value, the apparent size can be reconstructed, and spatial features can be mapped back into their original arrangement. The gravitational lens becomes a known layer that must be removed mathematically from the view. In this sense, the three images are not three separate discoveries. They are three records of one ancient system, each written by the same source and rewritten differently by the foreground gravity of Pandora's cluster. Their agreement allows astronomers to identify the common origin, while their differences reveal the action of the lens. By combining all three Webb observations, recover a more reliable picture of the distant object than any one image could provide alone. The source remains far beyond the cluster, but the cluster's gravity turns one faint signal into several measurable paths, preserving enough information for the ancient system to be studied with considerable scientific precision. Beyond the distortions created by Pandora's cluster, the reconstructed source is extraordinarily compact and deeply red in Webb's infrared view. Astronomers identify it as Abell 2074 QSO, 1 often shortened to QSO-1. It belongs to a class of distant objects informally called little red dots. The name is descriptive rather than theoretical. In Webb images, these sources appear small, faint and red, with much of their detectable light concentrated into an area that is difficult to resolve directly. Their appearance immediately raises a physical question about what produces so much radiation inside such a limited region. Little red dots become prominent in observations of the early universe because Webb can detect infrared light with sensitivity and resolution unavailable to earlier telescopes. Their red color does not necessarily mean that the objects contain the same kind of old stellar populations that make some nearby galaxies look red. At great cosmic distance, several effects can contribute. The expansion of the universe shifts shorter wavelength light into the infrared. Dust can absorb blue and ultraviolet radiation more efficiently than longer wavelengths. Strong emission from hot gas around an active black hole can also reshape the spectrum. The observed color is therefore the combined result of distance material and the physical processes generating the light. QSO-1 is especially useful because gravitational lensing increases its apparent brightness and stretches the source enough for Webb to recover spatial information that would otherwise remain hidden. After the lensing effects are modeled, the object remains intrinsically small. Its luminous central region occupies a scale far below that of a large, mature galaxy. The image does not reveal extended spiral arms, a broad stellar disk, or a large elliptical body. Instead, the system is dominated by a concentrated source whose radiation emerges from a very limited area. The word quasar is historically associated with extremely bright, active galactic nuclei. An active galactic nucleus is a compact region near the center of a galaxy where a black hole is gaining matter and releasing large amounts of energy. QSO1 carries a related designation because its spectrum shows evidence of energetic central activity. Yet it does not resemble the enormous luminous quasars often found in later cosmic history. It is fainter and smaller, and its host appears unusually slight compared with the mass concentrated at its center. Webb does not see the black hole itself. A black hole emits no ordinary light from inside its event horizon. What the telescope detects is radiation from matter outside that boundary. Gas falling toward a black hole can form a rotating structure and become heated as gravitational energy is converted into motion and radiation. Some of this light passes through surrounding gas, where atoms absorb or emit radiation at characteristic wavelengths. The resulting spectrum carries information about the environment near the compact object. For a little red dot, separating this central emission from the light of surrounding stars is difficult. Both components occupy an extremely small angle on the sky. Even with gravitational magnification, the stellar system can be only partly resolved. Astronomers therefore combine imaging with spectroscopy. Images reveal how concentrated the light appears, while spectra show which wavelengths dominate and which atomic features are present. Together, these measurements allow researchers to estimate how much radiation is likely associated with stars and how much may come from an active central source. QSO1 stands out because the central contribution is substantial. Its light cannot be explained comfortably as ordinary starlight from a large, mature galaxy. The object contains signs of rapidly moving and ionized gas near a compact gravitational center. At the same time, the surrounding stellar population appears modest. This combination makes the system different from the common arrangement in the nearby universe, where a massive black hole usually sits inside a galaxy containing much more mass in stars. The compact appearance also places limits on possible interpretations. A source that radiates strongly from a very small volume requires a mechanism capable of concentrating energy efficiently. Dense star formation can produce intense light, especially in young galaxies, but it leaves characteristic spectral signatures and usually distributes the emission across a region containing many stars and gas clouds. Accretion onto a black hole can concentrate far greater power into a much smaller region. The measurements of QSO1 are examined with both possibilities in mind because the early universe contains environments that do not always resemble nearby systems. Little red dots as a population remain an active area of research. Webb has revealed many more of them than astronomers expected before the telescope began observing. Some show evidence for active black holes, while others may have spectra strongly affected by dense gas dust or unusual stellar populations. The same visual category can therefore include objects with different internal structures. The label describes appearance, not a single confirmed physical model. For QSO1, the lensing geometry makes the classification more informative than it would be for an unresolved red point alone. The three images show consistent properties, and the reconstructed source remains compact after the foreground distortion is removed. Its infrared color is therefore not simply an artifact of the lens. Gravity changes brightness, position, and apparent shape, but it does not create the source's underlying spectral character. The redness also reflects the enormous journey of the radiation. Light, emitted when the universe is only about 700 million years old, is stretched as space expands. Radiation that begins at ultraviolet or visible wavelengths can reach Webb in the infrared. This shift allows the telescope to examine physical processes that occurred at wavelengths no longer received in their original form. Webb's instruments are designed precisely for this regime, where ancient light has been moved beyond the range of ordinary human vision. Within the reconstructed image, QSO1 therefore appears as a small system with a disproportionately intense center. Its size, color, and concentrated light establish the observational foundation for studying what lies inside it. None of these properties alone proves how the object formed. Together, however, they show that the ancient source is not simply a normal young galaxy seen at great distance. It is a compact, red, strongly lensed system in which central activity plays a dominant role, preserved in radiation that has crossed most of cosmic history before entering Webb's detectors. Once the lensing distortion is removed and the compact red source is reconstructed, attention settles on the faint stellar system surrounding the center of QSO1. The object spans only about 1,300 light-years. Within this limited region, Webb detects light that can arise from several physical components, including stars and the energetic material associated with the central source. Separating those contributions is essential because the amount of stellar mass determines whether QSO1 resembles an ordinary young galaxy with a growing central black hole, or a much more unusual system in which the central mass already dominates. Estimating the mass of stars in a distant galaxy normally begins with its light. Stars of different ages, temperatures, and chemical compositions produce characteristic patterns across the spectrum. Astronomers compare the observed brightness at different wavelengths with models of stellar populations and infer how many stars are required to create the measured radiation. This method works well when starlight dominates the continuum, the broad background of emission between individual spectral lines. In an active system such as QSO1, However, radiation connected with material near the black hole can imitate or conceal features that might otherwise be assigned to stars. Early studies of QSO-1 illustrate this difficulty. Its spectrum contains a pronounced change in brightness around wavelengths associated with hydrogen. Such a feature can sometimes be produced by a population of stars. If that interpretation is adopted, the infrared stellar mass becomes large. More detailed Webb spectroscopy shows that extremely dense gas along the line of sight can reproduce important parts of the same spectral appearance. This reduces the amount of continuum that must be attributed to stars and weakens earlier estimates based mainly on stellar models. The distinction matters because light does not measure mass directly. A compact system can contain bright material without containing a correspondingly large population of stars. Young massive stars can produce much more light per unit mass than older populations, while dust and gas can change how that light escapes. Radiation from an accreting black hole adds another layer. For QSO-1, the central source contributes strongly enough that ordinary methods of fitting the overall spectrum can overestimate the stellar component unless the active emission and gas absorption are treated carefully. Spatial information provides a second constraint. If a large mass of stars were distributed throughout the system, their collective gravity would influence the motion of material across the source. A galaxy containing many tens of millions or hundreds of millions of solar masses in stars would not behave gravitationally, like a nearly empty envelope surrounding one dominant point. The distribution of mass would be extended rather than sharply concentrated. Webb's ability to resolve the lensed source therefore allows astronomers to compare the light-based estimates with the gravitational effects of whatever mass is actually present. The newer measurements leave surprisingly little room for a massive stellar host. The stellar mass is constrained to less than about 20 million solar masses. This limit is not a simple count of visible stars. It emerges from combining the spatially resolved observations with models that determine how much distributed mass can exist without conflicting with the observed structure and motion of the system. The exact stellar content remains uncertain, but the available data do not support a host galaxy containing the much larger stellar mass that would normally be expected around such a substantial central object. The faintness of the host also affects the visual character of QSO-1. A mature galaxy with a large stellar population produces an extended glow that becomes easier to distinguish from a compact nucleus. In QSO-1, that extended stellar component is weak. Even after the natural magnification provided by Pandora's cluster, the continuum remains highly concentrated. The source, therefore, lacks the strong, broad stellar body that might otherwise surround the center. Its small apparent scale is consistent with a system whose assembled population of stars is still limited. This does not mean that QSO-1 contains no stars. The observations permit a stellar component and some star formation may be present. The important result is the upper limit on how much stellar mass can be hidden within the measured region. Because distant stellar populations can be faint, obscured, or difficult to separate from central emission, astronomers treat such limits carefully. The conclusion is not that every photon has been assigned perfectly. It is that a very massive stellar galaxy is difficult to reconcile with the combined evidence. The contrast with nearby galaxies is substantial. In the present universe, supermassive black holes generally occupy the centers of galaxies whose stellar mass greatly exceeds the mass of the black hole itself. The surrounding galaxy contains stars spread across thousands or tens of thousands of light years, forming bulges, disks, or elliptical structures. QSO-1 presents a different balance. Its surrounding stellar system is compact and light in mass, while a large amount of matter is concentrated close to the center. That imbalance changes how the system is described. QSO-1 is still associated with a galaxy because it contains a gravitationally bound environment in which stars and gas can exist. Yet the word galaxy can suggest a stellar structure more substantial than the observations actually require. In this object, the luminous host appears to be at an early stage of assembly. Its stars do not yet provide the dominant share of the measured mass across the central region. The uncertainty in stellar mass remains scientifically important. Models of distant populations depend on assumptions about stellar ages, dust star formation history, and the contribution of the active nucleus. Webb reduces these uncertainties by adding high-quality spectra and spatial information, but it does not remove them completely. Researchers therefore express the host constraint as a limit rather than as an exact inventory. Within that limit, the picture is unusually spare. A source only about 1,300 light-years across contains a faint stellar component whose mass is less than about 20 million times that of the Sun. The surrounding galaxy exists, but it is not the massive stellar structure that would normally be expected to accompany such an energetic center. The light from QSO-1 therefore records a stage of cosmic growth in which the stellar host remains small, compact, and only partly assembled. Inside the compact stellar environment of QSO-1, the material surrounding the central source is dominated by the simplest elements in the universe. Webb's observations indicate that the gas is composed almost entirely of hydrogen and helium, with only a very small contribution from heavier elements. This composition places QSO-1 among the most chemically primitive galactic environments measured at such an early time. Hydrogen is the most abundant element produced after the Big Bang. Helium is the second most abundant. Together they form the basic material from which the earliest generations of stars arise. Elements such as oxygen, carbon, nitrogen, silicon, and iron are created later through nuclear reactions inside stars and through events that return stellar material to space. Astronomers group these heavier elements together under the term metals, even though many are not metals in the everyday chemical sense. Metallicity is the measure of how abundant these heavier elements are compared with hydrogen and helium. In QSO1, the measured metallicity is less than about 0.5% of the Sun's value. This is an exceptionally low level. It does not mean that the gas is completely untouched by stars, because traces of heavier elements are still allowed by the observations. It does mean that the surrounding material has experienced very little chemical enrichment compared with the gas in mature galaxies. A star forms when cold gas becomes dense enough for gravity to overcome internal support. Once nuclear fusion begins in its core, the star starts converting lighter nuclei into heavier ones. The exact elements produced depend on the star's mass and evolutionary stage. Massive stars can build progressively heavier nuclei before ending their lives through powerful explosions or direct collapse. Lower mass stars return enriched material more gradually through winds and later stages of stellar evolution. Across many generations, these processes raise the metallicity of a galaxy's gas. The Sun forms from material that has already passed through several cycles of stellar birth and death. Its chemical composition, therefore, contains the accumulated products of earlier stars. QSO1 is observed at a much younger cosmic age, when far fewer such cycles have occurred. Even so, many galaxies existing at similar times already show substantial enrichment. Star formation can proceed rapidly in dense young systems, and massive stars live only a short time before releasing newly made elements. The extreme chemical simplicity of QSO1 is therefore notable even within the early universe. Webb measures this composition through spectroscopy. Atoms and ions interact with light at characteristic wavelengths determined by their internal energy levels. When gas is heated or ionized, it can emit bright spectral lines. The relative strengths of these lines depend on abundance, temperature, density, and the radiation passing through the gas. Hydrogen often produces strong features because it is abundant, while oxygen and other heavier elements generate their own identifiable patterns when enough of them are present. In the spectrum of QSO, one hydrogen dominates, while the signatures expected from a chemically enriched stellar environment are weak. Webb's spatially resolved measurements reinforce this picture by mapping where different kinds of emission appear across the source. The observations allow researchers to examine the gas over distinct positions within the magnified system and determine whether strong, heavy element emission is hidden in one region while absent in another. Together, these measurements show that primitive composition extends across the observed gas, rather than one isolated patch. The maps indicate that the low metallicity is widespread across QSO1. There is no clear evidence for a large reservoir of highly enriched material associated with an established stellar population. Oxygen, which is commonly used as a tracer of chemical enrichment, is scarce compared with what would be expected in a galaxy containing many generations of stars and substantial stellar debris. This chemical result agrees with the faint stellar host inferred from the object's light and mass distribution. The absence of abundant heavy elements also constrains the amount of previous star formation. A galaxy that has converted large quantities of gas into stars over a long period normally accumulates enriched material unless that material is efficiently removed. Supernova explosions and stellar winds can push metals outward, and fresh gas flowing inward can dilute enriched regions. These processes make metallicity an imperfect record of total star formation. Even so, an environment as chemically primitive as QS01 is difficult to combine with a history dominated by extensive generations of ordinary stars. The gas remains luminous despite its simple composition. Hydrogen can glow strongly when exposed to energetic radiation. Ultraviolet photons can remove electrons from hydrogen atoms, creating ionized gas. When electrons later recombine with protons, they release photons at characteristic wavelengths. Collisions within warm gas can also excite atoms, producing additional emission. These processes allow a cloud made mostly of hydrogen and helium to shine brightly, without requiring a rich mixture of heavier elements. Dense gas can also reshape the radiation passing through it. Absorption by hydrogen can suppress parts of the continuum, while scattering can broaden or alter spectral features. Such effects matter in QS01 because earlier interpretations of its spectrum allowed more of the observed light to be assigned to stars. Better spectral information shows that dense gas can account for much of the unusual shape without demanding a large stellar population. The gas is therefore both a source of radiation and a filter through which central radiation travels. Its low metallicity also affects how the gas cools. Heavy elements provide many efficient ways for heated material to lose energy through radiation. Gas containing mostly hydrogen and helium has fewer cooling channels, especially over certain temperature ranges. The thermal behavior of such material can therefore differ from that of enriched gas in later galaxies. Instead, Webb reveals a compact system filled with chemically simple gas, under the influence of an intense central source. Hydrogen provides the strongest visible tracer of this material. Helium contributes much of the remaining ordinary matter, and heavier elements are present only at very low levels. The composition records a system in which stellar processing remains limited. QS01 is therefore not merely young because its light comes from an early cosmic time. Its gas itself retains a chemical state close to the simple material from which the first generations of cosmic structures emerge. The light from QS01 reaches Webb as a mixture of signals produced by stars' gas and the energetic material surrounding the compact central source. To separate these contributions, astronomers use spectroscopy, a method that spreads light into its component wavelengths. Webb's near-infrared spectrograph is designed for this task. Instead of recording only how bright the object appears through a broad filter, the instrument measures how that brightness changes across many closely spaced wavelengths. Each change carries information about the physical state of the distant system. The instrument works in the infrared because cosmic expansion has stretched much of the original ultraviolet and visible radiation from QSO1 into longer wavelengths. Features that leave the source at relatively short wavelengths arrive at Webb far deeper in the infrared. Without an instrument sensitive to this range, some of the most useful atomic signatures would fall beyond the reach of ordinary visible light spectroscopy. Webb therefore observes ancient processes in a form that has been transformed by more than 13 billion years of expansion. A spectrum can be imagined as a detailed record of brightness arranged by wavelength. Smooth regions form the continuum, while narrow or broad peaks and dips mark places where atoms and ions interact strongly with radiation. Bright peaks are emission lines. They appear when excited atoms or ions release photons at particular energies. Darker features can appear when material along the line of sight absorbs specific wavelengths. Because each element has its own pattern of allowed transitions, these lines act as physical identifiers. Hydrogen provides some of the strongest features in QSO1. Its spectral lines are especially useful because hydrogen dominates the gas and responds strongly to energetic radiation near an active central source. Helium contributes additional information. Heavier elements are much weaker, consistent with the low metallicity inferred for the system. By comparing the strengths of the lines, astronomers can estimate relative abundances, although these estimates also depend on gas temperature density and the shape of the radiation field. Density changes how spectral lines form. In thin gas, excited particles may have enough time to release photons before colliding with other particles. In denser gas, collisions can interrupt or alter these processes. Some spectral transitions become stronger, weaker, or suppressed as density rises. This sensitivity allows spectroscopy to reveal conditions that imaging alone cannot show. A red point of light may appear simple in a photograph, while its spectrum records a complex environment containing regions with very different physical properties. Ionization provides another layer of information. An atom becomes ionized when one or more electrons are removed. The amount of energy required differs from element to element and from one ionization stage to another. Highly ionized gas therefore indicates exposure to energetic radiation or high temperatures. Near an accreting black hole, intense radiation can ionize gas over a wide range of energies. The resulting spectral pattern helps distinguish central black hole activity from radiation produced only by ordinary stars. The width of a spectral line reveals motion. Gas moving toward the telescope shifts its light toward shorter wavelengths, while gas moving away shifts it toward longer wavelengths. When many gas clouds move at different speeds, their combined emission spreads a line across a broader range. Very broad lines can indicate rapidly moving material close to a compact gravitational source. Narrower lines can arise farther away or in gas, moving more slowly. The width does not provide a complete map by itself, but it places direct constraints on the speeds present in the system. QSO-1 benefits from Webb's ability to collect spectra across spatially distinct parts of the lensed source. This turns spectroscopy from a single averaged measurement into something closer to a physical map. Instead of mixing all of the light from the object into one spectrum, astronomers can compare one position with another. Differences in line brightness or wavelength can reveal how gas composition and motion change across the source. Gravitational lensing assists this work by enlarging the apparent structure enough for Webb to resolve features that would otherwise remain blended. The three lensed images provide an additional check. Although their apparent shapes and brightnesses differ, because the foreground cluster magnifies each path differently, their underlying spectral identity should remain consistent. Matching lines at the same redshift confirm that the images trace the same distant source. Differences caused by noise magnification or local contamination can be identified more easily when several views of the same object are available. Spectroscopy also sharpens the measurement of cosmic distance. The overall red color of a distant object provides a clue, but individual spectral lines allow a much more precise redshift. Once astronomers identify a known atomic transition and measure the wavelength at which it arrives, the amount of stretching can be calculated. For QSO-1, these measurements place the source at a redshift of roughly 7, corresponding to a time when the universe is only about 700 million years old. The same spectrum helps separate starlight from active nuclear emission. Stellar populations produce characteristic continua and absorption features, while gas close to an active black hole can generate strong emission lines and a different continuum shape. Dense hydrogen can also reshape the spectrum through absorption and scattering. Modeling all of these components together reduces the risk of assigning too much light to stars simply because the source is compact and red. The near-infrared spectrograph therefore acts as more than a device for measuring color. It turns the ancient light into a record of physical conditions. Hydrogen lines trace abundant gas. Weak, heavy element lines reveal primitive chemistry. Ionization patterns constrain the energy source. Line widths measure motion. Spatial differences show how those properties vary across the compact system. Redshift fixes the light within cosmic history. In QSO-1, these pieces begin to converge. The spectrum describes a small, chemically primitive environment exposed to a powerful central source, with gas moving fast enough to reveal strong gravity. The information remains encoded entirely in photons that left the system during cosmic dawn, yet the structure of those photons allows Webb to reconstruct density composition, ionization, and motion. across a source that would otherwise appear as little more than a faint red point. That record makes the source physically measurable despite its extraordinary distance and compact apparent size. Hydrogen provides the clearest tracer of gas across QSO1. Webb does not record only a single total hydrogen signal. Through spatially resolved spectroscopy, it can measure how the brightness and wavelength of hydrogen emission change from one part of the lensed source to another. The strongest hydrogen features arise when electrons and protons interact within ionized gas. Energetic radiation removes electrons from hydrogen atoms, producing free electrons and protons. When an electron later recombines with a proton, it can release energy through a series of transitions that generate characteristic spectral lines. Once cosmic redshift is accounted for, the same transitions can be identified in the infrared spectrum recorded by Webb. In a distant, unresolved object, all of this emission would normally blend into one average measurement. QSO1 is different because gravitational lensing stretches the source across a larger apparent area. Webb can therefore compare spectra from neighboring positions that correspond to different regions within the original system. The resulting map is built by measuring the intensity of a hydrogen line at many points across the reconstructed source. Brighter regions indicate places where more line emission reaches the telescope. This can reflect a greater amount of ionized gas, stronger illumination, higher density, or a combination of these factors. Fainter areas may contain less emitting material or gas under different physical conditions. The map is therefore not a simple picture of gas density alone. It is a view of gas whose brightness depends on both matter and radiation. The map, therefore, gives astronomers an unusually direct way to examine gas across a source from cosmic dawn, even though each resolved region still represents an average over many smaller structures. Even with that limitation, the spatial structure carries valuable information. If the hydrogen emission came only from one unresolved point, the map would remain sharply concentrated at the center after the effects of the telescope and lens were removed. Instead, the observed signal can extend across the source. This shows that ionized gas occupies a measurable region rather than existing only immediately beside the compact nucleus. The gas forms part of the wider environment of QSO1. The shape of the emission is influenced by the geometry of the source. Gas may occupy a flattened structure, an irregular concentration, or several connected regions. Webb measures the projected arrangement on the sky rather than the full three-dimensional form. Material lying in front of or behind the center can overlap in projection. Astronomers therefore interpret the map as a two-dimensional representation of a more complicated volume. The hydrogen distribution can also be compared with the continuum light. Continuum emission includes radiation from stars and from material associated with the active center. If hydrogen follows the same spatial pattern as the continuum, both signals may arise from closely related regions. If the line emission extends farther, it indicates that ionized gas occupies a broader area than the strongest continuum source. These comparisons help separate compact central radiation from more extended gaseous material. QSO1 is small enough that every resolved element of the map corresponds to a substantial physical distance. Webb is not tracing individual clouds or stars. It is dividing the source into larger regions whose combined light carries the average properties of many particles and structures. Gravitational magnification improves that scale, but the reconstruction still represents a coarse physical map rather than a photograph of fine detail. The three lensed images help verify the pattern. Each image is transformed differently by Pandora's cluster, yet all three trace the same underlying source. When the lens model is applied, corresponding structures should map back to a consistent distribution. Agreement among the reconstructed views increases confidence that a feature belongs to QSO1 rather than to noise contamination or an imperfect foreground correction. Hydrogen brightness also depends on the amount of energetic radiation reaching the gas. Regions exposed to a stronger ionizing field can emit more strongly if enough material is present. Dense gas can increase recombination rates because electrons and protons encounter one another more frequently. Very dense conditions can also alter the detailed behavior of spectral lines. The spatial map, therefore, combines information about structure with information about excitation. Dust can influence the observed distribution as well. Dust grains absorb shorter wavelength radiation and can hide parts of a source unevenly. QSO1 has very low metallicity, so the amount of dust may also be limited because dust is built from elements heavier than helium. Still, even a small quantity can affect light if it is concentrated along particular lines of sight. The observed map represents the gas after all such radiative effects have shaped the photons that escape. The value of resolved hydrogen emission lies in its ability to turn a compact red source into a physical landscape. Instead of treating QSO1 as a single point with one spectrum, astronomers can identify where line emission is stronger, where it weakens, and how the pattern relates to the central continuum. The source gains measurable internal structure. This structure is particularly important in a system with so little stellar mass. If stars formed a large extended galaxy, some of the gas might be distributed within a broad stellar body. In QSO1, the weak host means that the hydrogen map becomes one of the most direct ways to trace ordinary matter across the source. The gas reveals a component that can be followed even where starlight is faint. The map remains a reconstruction rather than a direct, untouched image. Every measured position has been affected by the telescope's resolution, the gravitational lens cosmic redshift, and the physical conditions of the emitting gas. Astronomers account for these effects through models and repeated measurements. Within those limits, the hydrogen emission shows that QSO1 contains a compact but spatially extended reservoir of ionized material. Across that small region, the gas preserves a visible record of where radiation and matter meet. Hydrogen atoms are repeatedly ionized and recombined, releasing photons that travel outward pass through the gravitational field of Pandora's cluster and eventually enter Webb's instruments. By mapping those photons position by position, the telescope transforms the faint source into a resolved field of gas. The result is a quiet but detailed portrait of the ordinary matter surrounding one of the earliest known active systems. Across the hydrogen map of QSO1, the gas does more than glow. Its spectral lines shift slightly from one position to another, revealing motion across the compact source. On one side, part of the emitting gas is displaced toward shorter wavelengths. On the opposite side, the line moves toward longer wavelengths. These paired changes show that one region is approaching along the line of sight while another is receding. Together, they form an ordered velocity pattern rather than a random collection of unrelated motions. The shift arises from the Doppler effect. When emitting gas moves towards the observer, the wavelength of its light becomes slightly shorter. When it moves away, the wavelength becomes slightly longer. The cosmic redshift of QSO1 moves the entire spectrum far into the infrared, but local motions within the source create much smaller shifts around that overall value. Webb can measure these differences and assign a line-of-sight velocity to different positions across the lensed image. Gravitational lensing is essential to this measurement. Without the magnification provided by Pandora's cluster, the emitting region would be much harder to resolve. The lens stretches the source across more detector elements, allowing the near-infrared spectrograph to compare the spectrum from one side with the spectrum from the other. Astronomers then use the lens model to reconstruct where those measured regions lie within QSO1 itself. The resulting pattern resembles rotation. Gas on one side moves predominantly toward the observer, while gas on the other side moves predominantly away. Between them lies a region where the line-of-sight velocity approaches the systemic value of the source, meaning the average velocity used to describe QSO1 as a whole. This smooth transition is expected when gas travels around a common center in an organized orbital structure. Rotation alone does not establish what lies at that center. Gas in ordinary galaxies also rotates because of the combined gravity of stars' gas and dark matter. The crucial information comes from how orbital speed changes with distance. Different distributions of mass produce different velocity patterns. If much of the mass is spread broadly through a galaxy, the gravitational pull experienced by orbiting material changes in a way that reflects that extended distribution. If most of the relevant mass is concentrated into a very small central region, the pattern becomes different. The gas in QSO1 follows a form close to Keplerian rotation. Keplerian motion describes orbits dominated by a compact central mass. The same basic behavior appears in planetary systems where the Sun contains nearly all of the mass controlling the planet's motion. Material closer to the central mass travels more rapidly, while material farther away moves more slowly. The precise observed velocities also depend on the orientation of the rotating structure relative to the line of sight. In QSO-1, Webb resolves this change across a region small enough for the central gravitational influence to dominate. The velocity field is consistent with gas orbiting a point-like concentration of mass rather than moving mainly under the influence of a broad stellar system. This is important because it relies on spatially measured dynamics. The conclusion does not come only from the brightness of the active source or from an empirical relation calibrated using lower redshift galaxies. Astronomers still have to account for the geometry of the gas. A rotating disk viewed nearly face-on would show relatively small line-of-sight velocities because most motion would occur across the plane of the sky. A disk viewed more nearly edge-on would display larger, approaching and receding components. The apparent shape of the source and detailed modeling of the velocity field help constrain this inclination. Uncertainty in the orientation contributes to uncertainty in the physical interpretation. Gas can also move for reasons other than rotation. Active galactic nuclei can drive outflows, sending material away from the center. Gas can fall inward, turbulent clouds can move irregularly, and mergers can create complicated velocity structures. Researchers therefore test whether these alternatives reproduce the observed spatial pattern. In QSO-1, the orderly gradient and its dependence on position are well described by rotation around a compact central concentration. The narrow emitting gas used for this mapping is especially valuable because its motion can be followed across the source. Broad emission lines arise from gas moving at much higher speeds, very close to an active black hole, but that region is generally too small to map directly at this distance. Spatially extended line emission provides a different approach. It allows gravity to be traced through the motion of gas at measurable positions rather than inferred only from an unresolved line width. The foreground lens introduces additional complexity. Every observed position and velocity must be carried through a model of the cluster before the intrinsic structure is recovered. Lensing changes positions and apparent sizes, but it does not create the Doppler pattern itself. Consistency among the multiple lensed images helps test whether the reconstructed velocity field belongs to the background source. The velocity map also differs from a simple image because each position contains a measured spectrum. Astronomers fit the hydrogen line at that location and determine its central wavelength, width, and brightness. Repeating this process across the resolved source builds a field of velocities. Small measurement errors remain, especially where the emission is faint, so the final interpretation uses the full pattern rather than treating any single detector element as decisive evidence for organized rotation. After these corrections, QSO-1 presents a remarkably simple, dynamical pattern for such a distant and young system. Its hydrogen-bearing gas behaves as though it is orbiting a dominant central point. The ordered motion provides a direct gravitational signature across the source, instead of relying only on the radiation produced near an active nucleus. Webb follows ordinary gas as it responds to gravity. At this stage, the motion itself is the central evidence. One side approaches, the opposite side recedes, and the orbital speeds vary with position in the manner expected when a compact mass dominates the potential. The gas acts as a tracer moving through an invisible gravitational field, carrying the imprint of that field in tiny shifts of wavelength. Across billions of years of travel, those shifts remain preserved in the arriving photons, allowing the internal motion of QSO-1 to be reconstructed from the infrared spectrum. The ordered motion of hydrogen across QSO-1 provides more than a map of rotation. It also provides a way to weigh the mass responsible for that motion. Gravity links orbital speed to the amount of matter enclosed within an orbit. When gas moves around a compact center, faster motion requires a stronger gravitational pull, while the distance of the gas from the center determines how that pull is translated into an enclosed mass. In QSO-1, Webb resolves both quantities well enough for astronomers to estimate the central mass through dynamics rather than through brightness alone. The method begins with the velocity field measured from narrow hydrogen emission. At many positions across the source, the center of the spectral line shifts slightly. Those shifts provide line-of-sight velocities. Astronomers then determine how far each measured region lies from the apparent center after correcting for the gravitational stretching produced by Pandora's cluster. The result is a relation between orbital speed and reconstructed distance. This relation is often called a rotation curve, although the small size and limited number of resolved elements in QSO-1 make it much more compact than the rotation curves mapped across nearby galaxies. If the gas is moving in nearly circular orbits, gravity supplies the inward acceleration needed to keep it from traveling away in a straight line. The required gravitational force depends on the orbital speed and radius. A large speed at a given distance implies a large amount of enclosed mass. When nearly all of that mass lies inside the innermost resolved region, the orbital pattern approaches the Keplerian form seen around a dominant central object. The observed decline of speed with increasing distance then provides a direct constraint on how concentrated the mass must be. This approach differs from simply estimating black hole mass from the luminosity of an active nucleus. Brightness depends on how rapidly matter is being accreted, how efficiently gravitational energy becomes radiation, how much light is absorbed, and how the radiation is oriented. Two black holes with similar masses can therefore have very different luminosities. Dynamics avoids much of this ambiguity because orbiting gas responds to gravity, whether the central object is radiating strongly or weakly. It also differs from the virial method commonly used for distant active black holes. In that method, astronomers measure the width of broad emission lines produced by rapidly moving gas close to the black hole and combine the line width with an estimate of the size of the emitting region. The relation is calibrated mainly with active galaxies at much later cosmic times. Earlier estimates of black hole masses in the young universe depend heavily on the assumption that these calibrations remain valid at such early cosmic times. The dynamical measurement makes fewer assumptions about how an early active nucleus resembles nearby examples. It still requires a physical model, but the model is tied directly to resolved motion. The gas is observed at known projected positions, its velocity is measured, and the gravitational field required to sustain the pattern is calculated. This makes the result a direct, dynamical mass measurement in the astronomical sense. It does not mean that every source of uncertainty disappears. One important uncertainty is inclination. Webb measures only the component of velocity directed toward or away from the telescope. If the rotating gas lies close to the plane of the sky, much of its true orbital motion is hidden from the measured Doppler shift. If the structure is tilted more steeply, a larger fraction appears along the line of sight. The reconstructed geometry, therefore, has to be fitted together with the velocities. Different plausible inclinations can change the inferred central mass. Spatial resolution also matters. Each measured region blends light from an area larger than the smallest physical structures within QS01. Opposing velocities can partly mix inside the same resolution element, reducing the apparent velocity gradient. Astronomers model this effect using Webb's point spread function, the characteristic way a point source is blurred by the telescope and instrument. The gravitational lens must be included as well because it enlarges the source unevenly in different directions. The lens model introduces another layer of uncertainty. The conversion from apparent position on the detector to physical position in QS01 depends on how mass is distributed through Abel 2074. Small changes in the reconstructed magnification alter the infrared distances between gas regions. Because orbital mass depends on both speed and radius, those positional uncertainties propagate into the final result. The presence of multiple images and many other lensed sources helps constrain the foreground model. Astronomers also test whether an extended distribution of matter can reproduce the observed motion. Stars, gas, and dark matter all contribute gravity. If enough mass were spread throughout QS01, the rotation pattern would reflect that extended distribution rather than a central point. The observed Keplerian behavior strongly favors a concentration of mass near the center. The weak stellar host and chemically primitive gas independently limit how much ordinary distributed matter can be present. Turbulence and non-circular motion require attention as well. Gas does not behave like a set of ideal test particles. Pressure, radiation, inflow, outflow, and local disturbances can change its velocity. The narrow hydrogen line contains information about velocity dispersion, which measures the spread of motions around the average flow. By fitting rotation and random motion together, researchers can determine whether the ordered gradient is strong enough to trace the gravitational potential reliably. After these effects are included, the dynamical model remains consistent with a compact central mass dominating QSO1. This is the central achievement of the measurement. The gravitational field is not inferred merely because the object is bright or because its broad lines resemble those of lower redshift active galaxies. It is detected through the organized response of surrounding gas. The measurement therefore turns motion into a scale for hidden matter. Tiny wavelength shifts become velocities, lensed angular separations become physical distances, and the relation between those quantities becomes a measurement of gravity. Webb cannot see the central darkness directly, but the hydrogen around it behaves as a set of natural tracers. Their paths reveal where the mass is concentrated and allow the central object to be weighed from its gravitational influence alone across this ancient and unusually compact system. At the center of QSO1, the resolved motion of hydrogen points to a compact mass of roughly 50 million times the mass of the Sun. This value does not come from seeing the black hole itself. The event horizon remains far too small and distant to image directly. Instead, the estimate comes from the way surrounding gas responds to gravity. The measured orbital pattern is consistent with a point-like source whose mass dominates the central region, making a supermassive black hole the simplest physical explanation. A black hole is defined by the presence of an event horizon, a boundary inside which light cannot escape. For a black hole containing tens of millions of solar masses, that horizon is tiny compared with the region Webb resolves in QSO1. The telescope therefore observes the environment outside the horizon rather than the boundary itself. Gas moving hundreds of light years away can still carry a clear imprint of the central gravity, just as planets reveal the mass of a star without requiring its interior to be seen. The dynamical analysis gives a central mass close to 50 million solar masses with an uncertainty of several tenths of a decade in logarithmic mass. The true value could differ by roughly a factor of 2, while remaining compatible with the observations. This uncertainty reflects the limited spatial resolution, the orientation of the rotating gas, the gravitational lens model, and the possibility that pressure or irregular motions contribute to the measured velocities. The result is therefore not an exact count of mass, but it places the central object firmly in the range of a massive black hole. Independent evidence supports the same interpretation. Earlier measurements use broad hydrogen emission lines produced by gas moving rapidly in the immediate environment of the active nucleus. The widths of those lines, combined with empirical relations calibrated in active galaxies, also imply a black hole containing tens of millions of solar masses. Those methods carry their own uncertainties because the geometry and physical state of broad-line gas in the early universe may differ from nearby examples. The agreement with the resolved dynamical estimate is therefore important. Two different approaches sensitive to different regions of gas lead to broadly consistent masses. The central object is classified as supermassive because its mass is millions of times greater than the Sun. The term describes mass rather than physical size. A black hole of this kind can contain an enormous amount of mass within a region that on galactic scales remains compact. Its event horizon would span a distance much smaller than even 1 light-year, while its gravitational influence can shape gas far beyond that boundary. The Webb measurements depend on this extended gravitational influence. The black hole is also active. Material outside the event horizon is releasing radiation as it loses energy and moves inward. This activity makes the center detectable across more than 13 billion years of light travel. The luminosity does not mean the black hole itself is glowing. Radiation comes from matter still outside the horizon, where gravitational energy can be converted into heat and light. Some of that radiation ionizes the surrounding hydrogen and helps create the spectral features used to examine the system. The amount of radiation also provides a separate check on the mass. There is a characteristic luminosity at which outward pressure from radiation acting on ionized material balances the inward pull of gravity under idealized conditions. This is called the Eddington limit. Active black holes can radiate below near or in some circumstances above this level for limited periods depending on how matter flows. Estimates for QSO-1 indicate that its current luminosity does not require an implausibly small central mass. A black hole of tens of millions of solar masses can produce the observed activity at a physically reasonable accretion rate. Mass is more fundamental than luminosity for understanding the central object because brightness can change. The flow of gas toward a black hole may vary over relatively short astronomical time scales. A massive black hole can become faint when little material reaches it, and a smaller one can appear unusually bright during a period of rapid feeding. Gravity, by contrast, continues to reflect the accumulated mass. The resolved orbital motion therefore provides a stable measure of what is hidden at the center. Other compact objects cannot easily account for the measurement. A dense cluster of ordinary stars would have to place an enormous mass inside a very small region while remaining consistent with the weak observed stellar light. Such a cluster would also be difficult to maintain dynamically under these conditions. The combination of a point-like gravitational potential active nuclear emission and broad hydrogen lines strongly favors a black hole. The conclusion does not rest on one isolated signature. Even so, the observations do not determine every property of the black hole. Its spin is not measured directly. Spin describes how rapidly the black hole rotates and affects the innermost stable orbits of accreting matter, but the available Webb data do not uniquely determine it. The exact structure of the inner accretion flow also remains uncertain. Dust, dense gas, and viewing geometry can alter the radiation that escapes. These unknowns affect interpretations of how efficiently the object converts in falling matter into light but they do not remove the dynamical evidence for a large central mass. The age of the universe at QS01 makes that mass especially significant. Only about 700 million years of cosmic history have passed when the observed light leaves the system. The black hole is therefore already substantial at a time when the surrounding environment remains compact and chemically primitive. This temporal fact is secure even though the earlier path by which the mass accumulated is not directly observed. Within the central region, Webb therefore reveals gravity dominated by an object near 50 million solar masses. Hydrogen traces its influence. Broad emission confirms rapid motion close to the nucleus, and the active radiation marks matter interacting with the deep gravitational field. The exact mass retains a measurable range of uncertainty, but the central conclusion remains stable. QS01 contains a supermassive black hole whose presence is established not by an image of darkness, but by the ordered motion and energetic response of matter surrounding an unseen compact center. The most unusual feature of QS01 appears when the central black hole is compared with the surrounding galaxy. The black hole contains roughly 50 million times the mass of the Sun, while the stellar component of the host is constrained to less than about 20 million solar masses. Even allowing for additional gas and other distributed matter, the compact central object accounts for at least about 2/3 of the measured mass within the region mapped by Webb. In this young system, the usual balance between galaxy and black hole is therefore reversed. In nearby massive galaxies, the stellar body normally outweighs the central black hole by a large margin. A supermassive black hole may contain millions or billions of solar masses, yet the surrounding galaxy can contain hundreds or thousands of times more mass in stars. The black hole occupies the center, but it does not dominate the mass of the galaxy as a whole. QS01 presents a different arrangement. Its stellar host remains faint, compact, and light, while the central black hole already holds a substantial fraction of its measurable mass. This comparison depends on two independent measurements. The black hole mass comes from the motion of gas responding to a concentrated gravitational field. The host mass comes from limits on starlight and from the amount of distributed matter that can exist without changing the observed rotation pattern. Both quantities carry uncertainty but point in the same direction. Increasing the allowed stellar mass within reasonable limits does not easily restore the familiar nearby relationship. The phrase 2/3 of the measured mass refers to the compact region that Webb and gravitational lensing allow astronomers to resolve. It does not mean that every particle associated with QS01 has been counted. Dark matter can extend beyond the luminous source, and gas may exist outside the region traced by the observed hydrogen emission. The result concerns the mass that influences the resolved inner dynamics. Within that measured region, most of the gravitationally important matter appears concentrated near the center. This distinction matters because galaxies are not bounded objects with sharp outer surfaces. Their dark matter halos can extend much farther than their visible stars, and diffuse gas can occupy large volumes around them. In an early system, these outer components may be difficult to detect. Webb therefore measures the part of QSO1, for which the light and gas motion provide direct constraints. The central dominance is secure within this compact inner system, while the mass of a larger surrounding halo remains less certain. Even with that limitation, the contrast is striking because the stars are so modest. A black hole of roughly 50 million solar masses sitting inside a host with less than about 20 million solar masses in stars produces a ratio very different from that of most mature galaxies. The central black hole is not a small addition to an already assembled stellar structure. It is one of the principal mass components in the region that can be observed. The low metallicity of the gas strengthens this interpretation. If QSO1 had already formed and processed a very large stellar population, more heavy elements would usually be expected in the surrounding material. Stellar winds and explosions return carbon, oxygen, silicon iron and other elements to the gas. The extremely primitive composition, therefore, fits naturally with a host whose stellar growth remains limited. The chemical evidence does not determine the mass ratio by itself, but it supports a system with little accumulated stellar history. The compact size provides another constraint. The observed source spans only about 1,300 light-years. A large mature galaxy can extend across tens of thousands of light-years with stars spread through a broad disk or spheroid. QSO1 contains no comparable stellar structure. In the reconstructed Webb image, its light remains concentrated, and the mass traced by rotation behaves as though it is centered strongly around one point. The result challenges a simple sequence in which a large galaxy forms first and only later grows a massive black hole at its center. Nearby galaxies often show relationships between black hole mass and properties of the surrounding stellar bulge. These relationships suggest that black holes and galaxies influence one another over long periods. QSO1 shows that such mature relationships are not necessarily established during cosmic dawn. At this early stage, the black hole can be proportionally much larger than the surrounding visible galaxy. This does not mean that every early galaxy has a dominant black hole. Webb observes a selected object that is detectable partly because its active center is luminous, and partly because gravitational lensing magnifies it. Other young galaxies at similar times may follow very different growth histories. QSO1 demonstrates that some early systems can reach an extreme black hole to host ratio. It does not establish how common that state is across the young universe. Selection effects, therefore, matter. Active black holes are easier to identify when they are feeding and radiating, while small inactive black holes can remain hidden. Strongly lensed objects are a special subset of distant galaxies. Astronomers must compare larger samples before deciding whether QS01 represents a rare pathway or one phase that many early systems experience. The observation provides one clear example rather than a complete census. Within QS01 itself, the mass imbalance is difficult to avoid. The weak stellar continuum, primitive gas compact dimensions, and resolved rotation all converge on the same physical picture. The host galaxy has not yet accumulated a large stellar body, while the central black hole has already reached tens of millions of solar masses. Gravity, therefore, places the black hole near the center, not only in position, but also in importance. The system appears less like a mature galaxy containing a comparatively small central black hole and more like a massive compact center surrounded by the beginnings of a galaxy. Most of the measured inner mass is already concentrated in that center, while the visible stellar structure remains visibly sparse. At roughly 700 million years after the Big Bang, QS01 preserves an arrangement in which the black hole is not merely embedded within the galaxy. Within the region Webb can measure, it is the dominant mass around which the young host is organized. Close to the central black hole in QS01, ordinary matter enters a region where gravity becomes the dominant source of energy. Gas that approaches the center does not usually fall straight inward. It carries angular momentum, so it tends to orbit while gradually losing energy and moving closer. The resulting flow can form a compact rotating structure around the black hole. As neighboring layers move at different speeds, internal stresses redistribute angular momentum and convert part of the orbital energy into heat. The gas becomes luminous before it reaches the event horizon. This radiation is what allows the central black hole to reveal its presence. The black hole itself remains dark because light cannot escape once it passes inside the event horizon. Matter outside that boundary behaves differently. It can become extremely hot and emit strongly across a wide range of wavelengths. The exact spectrum depends on the mass of the black hole, the rate at which matter is supplied, the geometry of the flow, and the amount of surrounding gas and dust. In QS01, much of the radiation that leaves the central region is shifted into the infrared by cosmic expansion before reaching Webb. The accreting material does not form a perfectly simple disk. Real flows can be turbulent, uneven, and variable. Gas may arrive in streams, clouds, or denser concentrations. Some material can circulate for many orbits before moving inward. Magnetic fields can help transport angular momentum through the flow, allowing some gas to lose enough rotational support to approach the center. These processes occur on scales far smaller than Webb can resolve directly, so their structure is inferred from the radiation they produce and from the behavior of gas farther out. As the central radiation passes through surrounding hydrogen, it changes the state of that gas. Energetic photons can ionize atoms by removing electrons. Recombination then produces bright hydrogen emission lines. Other atoms and ions respond at their own characteristic energies. The resulting spectrum therefore contains an indirect record of the radiation field generated near the black hole. Strong ionization can indicate a compact source capable of producing photons more energetic than those normally supplied by an ordinary population of stars. The gas nearest the active center can move at very high speeds. Its emission lines become broad because different parcels of gas approach and recede along the line of sight at different velocities. These broad lines arise from a region too small to map spatially in QSO1, but their widths show that gas is moving rapidly in a deep gravitational potential. Farther out, the narrower hydrogen emission traced across the source moves more slowly and can be resolved into the rotating pattern measured by Webb. This creates several nested layers of evidence. The innermost emitting gas reveals rapid motion close to the compact center. The broader, spatially resolved gas reveals ordered rotation farther out. The radiation field ionizes material across the system. Each layer responds to the same underlying source of gravity and energy, even though the physical conditions differ greatly with distance. Accretion also provides a way for a black hole to gain mass. Gas crossing the event horizon adds to the black hole, but not all of the material approaching the center necessarily reaches it. Some energy is radiated away and some gas can be pushed outward. Radiation pressure can oppose further inflow, especially when the luminosity becomes high. Outflows driven by heat, radiation, or magnetic fields can remove part of the available material. The rate at which the black hole grows is therefore not identical to the rate at which gas arrives in its surrounding environment. The efficiency of the process matters. If a large fraction of the gravitational energy is converted into radiation. Before matter crosses the horizon, the black hole can appear bright while gaining mass relatively slowly. If the flow radiates less efficiently, more of the incoming material can be added without producing the same amount of light. The efficiency depends partly on the structure of the accretion flow and on properties of the black hole, including its spin. For QSO1, these quantities are not measured precisely enough to reconstruct the full growth history. The observed luminosity represents only the state of the system when the recorded light leaves it. Active black holes can change their feeding rate over time. A bright phase does not prove that the object has been accreting at the same rate throughout its existence. Long intervals of weaker activity may alternate with episodes of stronger inflow. The ancient radiation preserves one stage of that changing process. The surrounding environment can help supply matter. QSO1 contains a reservoir of hydrogen-rich gas, and its compact dimensions place much of that material relatively close to the central gravitational potential. Gas can lose angular momentum through interactions, instabilities, and disturbances within the young system. Once enough angular momentum is removed, material can drift inward. The weak stellar host means that the gas is not embedded in a large, mature stellar structure, but gravity can still organize its motion around the dominant central mass. The very low abundance of heavy elements may also influence the accreting environment. Metal-rich gas can cool efficiently through many atomic transitions, while metal-poor gas has fewer ways to radiate energy at some temperatures. Dust which forms from heavier elements is also expected to be less abundant in such primitive material. These differences can alter how gas fragments cools and moves, although the detailed structure of the inner flow remains uncertain. Radiation escaping from the accretion region does more than reveal the black hole. It changes the physical state of the surrounding system. Ionized gas heats and cools differently from neutral gas. Strong radiation can suppress collapse in some regions while compressing material in others. Outflows can redistribute gas and energy. These effects are collectively described as feedback, but the strength and long-term importance of feedback in QSO-1 are not directly measured. The observations show an active source interacting with nearby gas, while the wider consequences remain uncertain. Within the innermost observable environment, the black hole therefore appears through the behavior of matter that has not yet disappeared from view. Gas orbits, heats, ionizes, radiates, and in some cases moves inward toward the event horizon. The emitted photons carry information about velocity, temperature, density, and energetic illumination. By the time this radiation reaches Webb, the black hole itself is still invisible, yet the surrounding accretion flow has transformed gravity into light strongly enough to expose the presence of the compact center across most of cosmic history. The mass of the black hole in QSO-1 places a strong constraint on the kind of object from which it could have begun. At the time recorded by Webb, the universe is only about 700 million years old, yet the central black hole already contains roughly 50 million solar masses. Its surrounding stellar system is small and chemically primitive. These facts do not reveal the birth of the black hole directly, because Webb observes the system long after the original seed forms. They do, however, restrict which formation histories can plausibly produce such a large central mass within the available time. Astronomers use the word seed for an early black hole that later grows into a much more massive object. One possible class is called a light seed. In this picture, an early massive star reaches the end of its life and leaves behind a black hole with a mass of perhaps tens or hundreds of solar masses. Such remnants can grow by accreting gas and by merging with other black holes. The mechanism is based on familiar stellar evolution, but the limited age of the early universe creates a demanding growth problem when the final object already contains tens of millions of solar masses. Growth by accretion is not instantaneous. Matter approaching a black hole releases radiation, and that radiation can push against surrounding gas. Under relatively steady conditions, this creates a natural scale for how quickly a black hole can gain mass while remaining luminous. A light seed can become very large if it forms early, receives a continuous supply of gas, and spends long periods accreting efficiently. Interruptions, feedback, and a limited fuel supply slow the process. Episodes of unusually rapid accretion can shorten the required time, but their duration and prevalence in the first galaxies remain uncertain. A second class begins with a much larger seed. Heavy seed models produce black holes containing thousands to hundreds of thousands of solar masses, or in some scenarios even more. Starting from a larger mass reduces the number of growth stages required before the object reaches the scale observed in QSO-1. Several mechanisms have been proposed, but direct collapse of gas is among the most extensively studied. Direct collapse begins with a large concentration of primordial or nearly primordial gas. Instead of fragmenting efficiently into many ordinary stars, the cloud remains warm enough and coherent enough for a large amount of material to move toward one central region. If fragmentation is strongly suppressed, the central concentration can become extremely massive. Depending on the detailed pathway, it may briefly pass through a supermassive stellar state or collapse more directly into a black hole. The result can be a seed far heavier than the remnant of a single normal star. Creating those conditions is difficult. Hydrogen gas naturally cools as it radiates energy, and cooling encourages fragmentation into smaller clumps that can form stars. A direct collapse environment therefore requires processes that keep the gas from breaking apart too early. Strong ultraviolet radiation from nearby sources can reduce the formation of molecular hydrogen, an efficient coolant in metal-poor gas. Rapid inflow turbulence and the structure of the host dark matter halo can also affect whether one large concentration forms instead of many smaller stars. Chemical purity matters as well. Carbon, oxygen, and other heavy elements provide additional cooling channels. Dust can cool dense gas and encourage fragmentation. A cloud with extremely low metallicity is therefore more favorable to some direct collapse pathways than a cloud that has already been strongly enriched by previous generations of stars. QSO-1 contains gas with remarkably few heavy elements, which is consistent with a chemically primitive environment. This agreement makes direct collapse physically interesting, but it does not prove that direct collapse occurred. The small stellar mass offers another clue. If the black hole began as the remnant of a long sequence of ordinary massive stars, substantial star formation might be expected in the surrounding system. QSO-1 instead contains a black hole that outweighs its observed stellar host. A heavy seed can more naturally create a stage in which the black hole becomes important before a large stellar galaxy has assembled. Models of such systems can therefore reproduce unusually high black hole to stellar mass ratios more easily than some simple light seed histories. Mergers may also contribute. Early dark matter halos collide and combine, frequently bringing gas stars and any central black holes together. Black holes can eventually merge after their host systems combine, adding mass without requiring every increase to come from gas accretion. The efficiency of this process depends on how often suitable seeds form and how rapidly they sink toward common centers. Mergers alone do not identify the original seed because both light and heavy seeds can participate in later mergers.
More speculative possibilities include primordial black holes formed from unusually dense regions
In the very early universe under conditions present during cosmic dawn itself. Such objects would not require stars to exist first. Primordial black holes remain hypothetical, and observations have placed strong limits on how abundant they can be across many mass ranges. QS01 does not provide direct evidence that its central object is primordial. The possibility can be tested within theoretical models, but it remains substantially less established than the existence of the black hole itself. The present observations, therefore, separate evidence from origin. Webb directly supports a massive central object, a weak stellar host, primitive gas, and an age of about 700 million years after the Big Bang. The telescope does not record the moment when the seed appears. Heavy seed pathways, especially direct collapse of a large metal-poor gas cloud, provide a plausible way to reduce the required amount of later growth. Light seeds remain possible under sufficiently rapid and sustained growth conditions. Primordial scenarios remain speculative. The birth of QS01's black hole is therefore constrained without being reconstructed. Its large mass requires an efficient early pathway, while its chemically simple and star-poor environment favors models in which substantial black hole growth begins before extensive stellar assembly. The ancient system preserves the outcome of that process rather than the process itself, leaving formation models to be judged by how well they reproduce the measured mass-age chemistry and unusually small stellar host. The structure of QS01 brings the central question into its clearest form. At roughly 700 million years after the Big Bang, the system contains a supermassive black hole of about 50 million solar masses, while its observed stellar host remains much smaller. The black hole accounts for most of the measured mass within the compact region mapped by Webb. This arrangement is consistent with a stage in which substantial black hole growth occurs before the surrounding galaxy has assembled a large population of stars. The phrase "formed before its galaxy" requires careful meaning. A black hole cannot be placed outside all surrounding matter, and QS01 already contains gas and some stars. The observation, therefore, does not show a black hole existing in complete isolation before any galactic structure exists. Instead, it shows that the central black hole may reach a very large mass before the stellar component normally associated with a mature galaxy becomes dominant. In this sense, the order of growth appears different from the simple picture in which a large stellar galaxy forms first and gradually builds a much smaller black hole at its center. Nearby galaxies often display correlations between the mass of their central black holes and properties of their stellar bulges. More massive bulges tend on average to contain more massive black holes. These relationships are not exact, but they suggest a long history of connected growth. Gas can feed both star formation and black hole accretion. Stellar winds, supernovae, and radiation can reshape the gas supply, while an active black hole can heat or expel material from the central region. Over billions of years, these processes can bring the growth of a black hole and its host into a more regular relationship. QSO1 is observed before such a mature balance is established. Its stellar population is too small to fit comfortably onto the common relationships measured in the nearby universe. The central mass is already disproportionately large. This does not invalidate the later correlations. It instead suggests that those correlations may emerge through evolution rather than being fixed at the moment when the first black holes and galaxies appear. A young system can change substantially after the light observed by Webb leaves it. Gas may continue to fall into the surrounding dark matter halo. New stars may form. Smaller galaxies may merge with it. The black hole may experience additional episodes of accretion, while the stellar mass of the host may grow even more rapidly. If stellar assembly eventually catches up, a black hole-dominated system can move toward a mass ratio more similar to those seen at later cosmic times. The observation captures one early state rather than a final configuration. The low metallicity of QSO1 supports this interpretation because the gas has undergone relatively little processing inside stars, a system that already contained a long-lived, massive, stellar population would generally return more heavy elements to its surroundings. The chemical simplicity, therefore, fits with a host still early in its stellar development. At the same time, metallicity can be affected by inflowing pristine gas and by outflows that remove enriched material, so chemistry alone cannot determine the sequence of formation. The dynamical measurement provides the strongest part of the argument. Gas orbiting the center reveals a concentrated mass that cannot easily be explained by the faint stellar host. The black hole is therefore not inferred only from brightness or from unusual color. Its gravitational influence is spatially resolved. This makes QSO1 a particularly important example because the central mass and surrounding stellar component can be compared within the same compact system using several independent forms of evidence. The result also changes how early black hole growth is tested. Before Webb, very distant quasars already demonstrated that billion solar mass black holes exist less than a billion years after the Big Bang. Those objects create a timing problem, but their bright nuclei often make the host galaxies difficult to measure. QSO1 offers a different kind of constraint. Its black hole is less massive than the largest early quasars, yet gravitational lensing and Webb spectroscopy allow the surrounding system to be examined in unusual detail. The imbalance between black hole and host can therefore be measured rather than assumed. Even so, one object cannot define the history of all early galaxies. QSO-1 is detected under favorable circumstances. Its central black hole is active, its radiation is strong enough to be identified, and Pandora's cluster magnifies the source. Other systems containing smaller or inactive black holes may remain below current detection limits. A population selected through bright active nuclei may naturally emphasize objects with unusually prominent black holes. The frequency of black hole first growth, therefore, remains uncertain. Larger samples are needed to determine whether QSO-1 represents a rare pathway, a brief developmental phase, or a common feature of cosmic dawn. Webb is beginning to identify more compact red sources and active black holes at high redshift, but their physical properties are diverse. Some may contain massive black holes, while others may be dominated by stars or dense gas. Precise dynamical measurements like the one possible for QSO-1 remain difficult because most distant sources are too small and faint to resolve in comparable detail. The distinction between observation and interpretation therefore remains essential. The observation establishes an early supermassive black hole, a small stellar host, primitive gas, and a central mass fraction far above that of typical mature galaxies. The interpretation that the black hole grows before most of its galaxy is a physically reasonable description of those measurements. The deeper claim that black holes generally form before galaxies is not established. QSO-1, instead, provides a direct example of cosmic growth proceeding in an unexpected order. A massive compact object is already in place while the surrounding stellar system remains limited. The galaxy is present, but much of its later stellar structure has not yet accumulated. In this ancient source, Webb records a moment when the central darkness appears to be ahead of the galaxy around it, preserving evidence that the first massive black holes and the first substantial galaxies do not always have to grow together at the same pace. That uneven timing becomes a clue to how rapidly gravity organizes matter during the first billion years of cosmic history.